Hello everyone and welcome back to Diksha Karnataka YouTube channel, and you are watching KCET 60 out of 60 in physics series, where we are discussing each chapter concept wise. We have already completed so many chapters. Today we are continuing with alternating current part 2. We have already completed alternating current part 1. If you have not yet watched that, don't forget to visit our channel and watch that part. So today we are basically going to discuss mainly about LCR connection, different connections, then resonance, important concept, and transformers. Okay, these three will be our primary topic, and all the class notes, all the updates will be available on our WhatsApp channel. So for that you have to join our WhatsApp channel. The link is given in the description below. So you have to follow our WhatsApp channel. There you can get all the update related to KCET 2025. Now let's look into the list of contents that we are going to discuss today. So we will start with RL circuit, then we will move to RC circuit. Okay, some people, instead of calling it RL circuit, they call it LR circuit. Both are fine. Okay, similarly RC circuit is also called CR circuit. That is also fine. Next we will talk about LCR series circuit, the most important concept of this chapter. Then we will also talk about resonance, another very important chapter. Some part from this chapter, this part is deleted, that also we will discuss that this part is deleted. You don't need to focus on those concepts. Next we will talk about power in an LCR circuit, and then lastly we will discuss about transformers. Okay, so everything will be discussed in this lecture, and as promised we will complete the chapter today, and we will move on to PYQs for this chapter tomorrow. Right, let's move on to RL circuit. What is RL or LR circuit? When one resistance and one inductor are connected in series. So we are only interested in series circuit. Okay, parallel combination is not there in your syllabus, so we are not even going to discuss parallel combination. Also LC circuit is no longer part of your syllabus, so LC circuit, LC oscillation, that also we are not going to discuss in our discussion, because this is focused mainly towards KCET. So we are trying to understand what all the questions, what are the concepts coming in KCET, so our focus will be solely towards KCET. Now this LR circuit directly is not part of your syllabus, but this is very important to understand LCR circuit. That's why I have included LR and RC circuits in my discussion. Formulas and etc. Can be derived from LCR series circuit. Sometimes the question comes as even though it is not directly related to LR circuit, but they give you the question such that it is basically can be solved from LCR series circuit. But before understanding LCR series circuit, we have to understand what is RL circuit. Here one resistance, one inductor connected in series, and there is a AC source of voltage VT. Let's understand this in detail. So inductors and resistances are connected in series are called RL circuit. Now what is the impedance? Now here, instead of using the term that we are used to, resistance, in this chapter, from this chapter onwards, we will use a term called impedance. Impedance is nothing but AC version of resistance. Okay, impedance is nothing but AC version of resistance. Okay, now in case of DC, only a resistor is there. Okay, everything else is not does not matter. Okay, for example, in DC circuit, L can be considered as closed circuit. Okay, it is just acting as a conductor after initial few seconds. Then similarly capacitor, after few seconds you can consider it as an open circuit. Capacitor does not conduct in DC. Only if AC is connected, then only it allows the AC to pass. Now you should remember that capacitor and inductor works only in AC connection. Okay, that's why the term that we use is impedance. Impedance is we will see what is impedance is. So for RL circuit, impedance is R plus XL. Now what is XL? If you remember, XL is omega L. right? Omega is the frequency of the source, L is the inductance, self inductance of the coil. So together we can write this. Also sometimes we use this formula 2 pi f L. 2 pi f is nothing but frequency. Okay, I think in my last class I used the symbol nu. You can use nu, you can use f, whatever is familiar with. Okay, 2 pi f L, right? Now what is the current flowing in a circuit? Current flowing in a circuit is Vm sin omega t, that is V by R. So V by R is nothing but V by Z. Instead of using V by R, we will use V by Z symbol now, and from there we can write Im sin omega t. Now what is Im? Im is nothing but Vm by Z, right? Vm by Z, and from this expression you can see that current and voltages are in sync, that is they are in phase, right? In our RL circuit now no phase change happens. Okay, so phase, they are still in the same phase. Now look into the RC circuit. RC circuit is same. Okay, instead of inductor, we are now connected one resistor and one capacitor in series. Okay, simple, one resistor, one capacitor in series. Similarly, if we construct the expression, we can see that instead of omega L, here we have to write 1 by omega C. 1 by omega C. Omega C is the inductance of capacitor, right? We have already told you that this is the inductance, sorry, capacitance. Capacitive reactance we call the term. So similarly here there will be one F. Okay, so 2 pi fc, that is also sometime used. We will see that now. Similarly we can find the current in this case, right? Now let's move into our homework problems from yesterday. In Karnataka, the normal domestic power supply AC is 220 volt 50 hertz. Not only in Karnataka, in all over India the power supply is 220 volt 50 hertz. Okay, it is nothing to related to Karnataka in special, it is special in India. Okay, in USA the voltage is different, the frequency is different, they use 110 volt 60 hertz, but in most countries either 110 volt 60 hertz or 220 volt 50 hertz is used. Okay, in European countries also 220 volt 50 hertz is used. Now here what is the meaning of this 220 volt and 50 hertz? Now 50 hertz is the frequency that we know. Okay, frequency means not angular frequency but frequency f. That's why we use the formula 2 pi fl or 1 by 2 pi fc. Okay, so that is the reason, because when we are solving problems we can directly replace f into that formula. That's why that formula was given to you. Now what is the value, what is the meaning of this 220 volt? This represents RMS value. This represents RMS value of the voltage, okay, and frequency. Okay, so the correct answer is option B. Okay, this is not mean value, not peak value. Okay, so this represents RMS value. The value that is given is RMS value. The peak value is higher than that. I told you one question yesterday that can you answer why AC is more dangerous than DC? Because actually if you see 220 volt AC, 220 volt AC is actually 220 volts times root 2. Okay, which is about 300 and something, right? So that is the actual peak value of AC. So even if you are using 220 volt AC and 220 volt DC, 220 volt DC means its peak value is 220 volt, right? And but 220 volt AC means it is 220 volt times root 2, which is much higher than 220 volt. So actual peak value is much higher compared to that of 220 volt DC. That's why it is dangerous. Okay, now let's move on. The RMS value of current in a 50 hertz AC circuit is 6 ampere. So RMS value is given, IRMS is given is 6 amperes. Okay, the average value of AC current over the cycle is, so what is the average value of AC current over the cycle? Now it is given 50 hertz, right? Now we know that suppose the current is Im sin omega t, right? If they are in the same phase or opposite phase, now what is the average value of current? okay, does not have don't have anything to do with IRMS. Average value of current will be I average, which is nothing but Im sin omega t average. What is the value of sin omega t average? I told you yesterday, sin omega t average value is 0. So average value is 0. So average value of current is 0. Remember that, not always, but if this is a sine function, sine current, then it is always 0. Remember that part. Now let's move on. Now we are talking about series LRC, okay, or RLC, whatever CLR, you can change it anytime, but LCR is the most commonly used term, so I have used LCR, okay. Some used RLC also fine, okay. Now RCL, some use RCL because that is the order given, okay, so that's why people use it RCL, okay. I use LCR, fine. Now, so here we have an AC source, here we have one resistance, one capacitance and one inductor connected, all connected in series. As I said, we are only going to discuss about series connection, so they are connected in series. Now what we have to find? We have to find the current, we have to find the relationship between current, all these components. So let's look into them one by one. So first of all, if you consider all the potentials across each component, so the external applied potential is V. So externally applied potential, say V, okay, small v, and then potential across resistance, capacitance and inductance should be equals to V, right? So resistance across inductance is potential drop across the inductance is L di by dt, that is the induced EMF. Q by C, Q is equal to CV, so Q by C is the potential across the capacitance and V is equal to IR. So that is the voltage drop across the resistance, or in the other words we can write VL plus VC plus VR is equal to plus V. Now here in some of these terms may come out to be negative, okay, but we are not considering sign here. When we are adding that value, that will be automatically give us the sign, so don't worry about sign in this expression. You just need to know that individually if you add the potential drop across each components, then you should get the applied voltage, that is the Kirchhoff's voltage rule, KVL, right? So according to Kirchhoff's voltage rule, this is still applicable in this case, right, even though we are using AC. Now if you are considering the AC components, okay, along with their signs etc., then you can write this as V square is equal to VR plus, there is a mistake here, here will be, okay, VL minus VC whole square. Now VL and VC are opposite in phase, okay, so they have a total phase difference of 180 degree. So since they are in phase difference of 180 degree, while finding the average voltage between them, then you have to do VL minus VC, that is the formula. So similarly you can write this for this. Here also it is wrong, okay. Now you can write this as R square XL minus XC whole square. So this is the expression for impedance. So impedance can be calculated using this formula. And if you are wondering, these notes will be available in our WhatsApp channel as well as in the comment below. You can download the notes from there, okay. If you have any questions, you can comment that in the below. I will try to answer. So this is the formula for impedance. Impedance in an RLC circuit or LCR circuit is given by this formula. So R square plus XL minus XC whole square, okay. So this is the, and square root of that gives you the impedance of this circuit, right? Now in a series LCR circuit, R is given as 300 ohm, L is given as 0.9 Henry and C is given as 2.0 microfarad and omega is given 1000 radian per second. Then impedance of the circuit. This is from your previous year questions. So don't think that this is question I have manufactured. So you have to calculate the impedance of the circuit. So how can we do that? We know that impedance of the circuit is nothing but R square plus XL minus XC whole square, right? Let us first calculate XL. What is XL? XL is omega L. Okay, as long as it is given radian per second, you are fine. If it is not given in radian per second, if it is given RPM, then you have to convert it into radian per second formula. I hope you remember that, how we can do that. Otherwise, while doing rotational motion, circular motion, I will teach you back that again. So till that point of time, you because it is given directly in radian per second, I can use that. So it is 900, okay, 900 ohm. Now what is XC? XC is 1 by omega C, right? Now omega is 1000 and C is 2 microfarad. Microfarad means 10 to the power of minus 6. So it will be, so XC can be written as, see, 10 to the power 1000 means 10 to the power of plus 3, 10 to the power of minus 6. So we can write this as 2 times 10 to the power of minus 3, right? So this will go up, 10 to the power of 3 divided by 2, that is 1000 by 2, that is 500. So 500 is the XC. Now what we have to do, we have to use this formula. R is already given, 300 whole square plus XL is 900, XC is 500. So it will be 3 3s are 9, 1020, 1020 plus it will be 400 whole square. 400 whole square means what? 4 4s are 16 and 4 zeros, right? So if you add them, you will get 25 1020 1020. Okay, so if you square root them, you will get 25 is 5, then for 2010 or 20 one other 0. So 500 ohm is the impedance of the circuit. Correct answer is option A. Simple problem, very simple and easy problem if you know how to solve this. Now, in some books and in during some of the calculations, you might find that XL is less than XC. Okay, so in this formula, we received that XL is greater than XC. Okay, in your textbook and in some of the calculations, you might find XC is greater than XL. Don't worry, because there is a square available outside, even if the resultant term is negative, the square of that will become positive. So don't worry if it is written XC minus XL, okay, or XL minus XC. I know some of you are started writing in the comments saying that, sir, in my book, in my textbook, it is given XC minus XL. How you can say it is XL minus XC? It does not matter, because there is a square here, okay, and I will explain the meaning of why if XL is greater than XC, XC is greater than XL. I will explain that in a while. Now, let's solve one more numerical. In the given circuit, the peak voltage across capacitor, inductor and resistors are 30 volt, 110 volts and 60 volts, okay, respectively. The RMS value of the applied voltage is. Now, what is the voltage is 30, 110 and 60. So, what is the total voltage? Let us calculate the peak value of the voltage. Peak value is Vm. Remember that V is equal to Vm sin omega t. So Vm is the peak value. Okay. Now peak voltages across each component is given. So what is the peak voltage? We already know that Vm is addition of all the peak values, right? In case of RMS, it should be addition of all the RMS values. So you can convert them RMS for each individually, then you can add them up, or like the way I am doing, I am finding the total peak value of the input voltage. So peak value of the input voltage, suppose the input voltage is Vm sin omega t. So I am just trying to calculate the Vm. It is 30 plus 110 plus 60, so it will be 90, 200. 200 is the 200 volt is the peak value, right? So what is the RMS value? We know that RMS value is nothing but peak value divided by root 2. So it is 200 divided by root 2. Now if you calculate that, it will come around 1.141. Okay, now you can guess that value after calculating this. This is root 2. Root 2 is less than 2, right? So it cannot be 100, it should be more than 100. So 100 and 70 are cancelled. Obviously this is not 200, so other option left is 141.1. Actually the value is 141.1, but from the given option 141 is the correct answer. So you can write this as the correct option. So if you solve the answer, if you understand the mathematics, if you understand the numbers, you don't need to use any calculators. You can still solve it without using any calculators. Now let's look into this condition. Okay, so Im is equal to Vm divided by R square XL minus XC whole square, right? So we have already understood that, we have applied that, we have solved some problems. Now what will happen if the value of XL and XC are equal? What will happen if the value of XL and XC are equal? If XL equals to XC, then you can see that this term will become 0. If XL equals to XC, then this term will become 0. So the current will be simply Vm by R. That is like our Ohm's law. Remember our old Ohm's law? In old Ohm's law, it was V is equal to IR. So we are getting back our old Ohm's law formula. Even if there are capacitors connected, even if there is inductor connected, if somehow the inductance and capacitance are chosen such that the inductive reactance and capacitive reactance, they are equal, then the circuit will simply become a resistive circuit. This is the maximum current in the circuit. This condition is called resonance. Very important, super important. This condition is called resonance. So at this point, so if you choose the values of, there are three factors involved. Obviously, if you see, so at the resonance, suppose the corresponding frequency is omega naught or omega 0. So we can write that XL equals to XC, XL is omega naught L and XC is 1 by omega naught C. So from this you can find the value of omega naught, which is nothing but 1 by root over LC. So how you obtain that? If you say you can multiply omega naught C is equal to 1 by omega naught L. So take this here, take that omega up, so you will get omega naught square. Omega naught square equals to 1 by LC. So from there you can find omega naught is 1 by square root of LC, right? So this is the resonance frequency. If the frequency is chosen such that its value is actually 1 by LC, then the circuit no longer remains LCR circuit, is simply becomes a resistive circuit. So all the other parts will be cancelling each other. So whatever the voltage, positive voltage drop across the capacitor, the same voltage drop will be across the inductor and they will cancel each other. So you can simply calculate the resistive frequency, right? Now, so the phase difference between capacitor and inductor is given by XL minus XC divided by R. So current can be written as Im sin omega t plus phi. Now at resonance, at resonance, this is the phase difference for any other condition. At resonance, as you can see that XL minus XC becomes 0, right? So tan inverse 0 is phi equals to 0. At resonance, the phase difference becomes 0, right? So you can say that I becomes Im sin omega t. So at resonance, the current and the voltage are in phase. Okay. Now this is the graph for resonance. If you see, so for different values of omega naught, okay, if you see along this axis omega is plotted, along this axis I is plotted, okay, current is plotted. So if you change the value of omega, okay, you will get resonance value at some point, okay, and then you will get the maximum current for different R's. Okay, here I1 and I2 represent two different values of R, and this resonance frequency is independent of the value of R. That's what they are trying to show. As long as L, C and omega are related by the formula that I have shown, resonance frequency will remain unchanged. It is independent of the value of R, does not depend on the value of R. Now let's move on to solve one more problem. 3 readings of ammeter and voltmeter in the following circuit are respectively. Okay, so they have given you the values of VL 50 volt, VC 50 volt and R 100 volts. Okay, let me clear that if you are not able to see that. VL is 50 volts, VC is 50 volts and R is 100 volts. Okay, now what they have asked you, the readings of the ammeter and the voltmeter that you have to find. Okay, so basically you have to remember that, and the apply voltage is given 220 volts, okay, 50 hertz. Now here you can see from this expression VL equals to VC, right, magnitude wise. Now this happens only at resonance. Only at one point this condition is possible, that is when there is a resonance. Now at resonance, what is the most important thing? VL and VC, they will cancel each other. Okay, VL and VC are opposite phase. That means if VL is plus 50, VC will be minus 50. Similarly, VC is plus 50, VL will be minus 50. So they will cancel each other out. So they will, you can simply ignore this fact. So as long as they are same, you can ignore L and C completely. You can simply consider this as a circuit of simple resistance with a AC circuit. Okay, so what is the current? Current is, now readings of ammeter and voltmeter, they generally read RMS values. Okay, that is important. So ammeter and voltmeter, that is also one of the important values, is that when you are adding an ammeter, you are adding a voltmeter. It does not measure peak value, it does not measure any other value, it only measure the RMS value. So you have to find the RMS value. Let us find the peak value first. Peak value of voltage is here not voltage, RMS value is already given, right? So 220 volt, as I said before, V RMS is 220 volts. So the voltmeter will read 220 volts as it is. Okay, because if you add a voltmeter here, it will measure whatever voltage is coming from this. So voltmeter reading will be 220 volt. Now what is IRMS? IRMS will be VRMS divided by R. So that is 220 volt divided by 100 ohms. So it will be 2.2 ampere. So 2.2 ampere and 220 volt is the current and voltage measured by the ammeter and voltmeter. Simple question. So only the hint that you have to take from this is that VL and VC's values are given equal. That means it is in resonant condition. So that is basically they are in resonance condition. So if you are wondering, value of L is not given, value of C is not given, how can I find current, how can I find voltages? Don't worry, this is a resonant condition. So you can ignore inductor and capacitor in this case and simply use normal Ohm's law to find current and voltage. Now before moving into power, I just want to give you some hint, is that when XL is greater than XC, okay, when XL is greater than XC, we say the circuit is inductive circuit. Okay, circuit is inductive circuit. Circuit is inductive. And when XC is greater than XL, then that is a capacitive circuit. Okay, when XL equals to XC, the circuit is in resonance condition. If XL is greater than XC, then inductor is dominating. That means it is an inductive circuit. If XC is greater than XL, then capacitance is dominating. We call it a capacitive circuit. The simple thing. Okay, so I told you I will mention what is the meaning of this XL, XC, how if they are greater than one another, then what will happen. So this is the fact. Now let's move into the power of LCR circuit. Power. So now we have seen in case of pure inductor, pure capacitor, the power consumed was 0. Now what will happen in case of LCR circuit? Okay, is the power consumed be 0 in this case as well? So let's see. Power is Vodafone Idea, we know the formula. Okay, and heat developed is VIT, vitamin. So power is Vodafone Idea, we have applied Vodafone. So Vodafone is Vm sin omega t, we have put the values. Current is Im sin omega t plus phi, we have already discussed that. So current is I omega t plus phi when the phi is not 0. Now if you calculate that, you can take this as 2 sin theta, 2 sin alpha sin beta. Now what is the formula for that? Cos alpha minus beta minus cos alpha plus beta. If you remember the formula for sin alpha sin beta, it is cos alpha plus alpha minus beta, okay, minus cos alpha plus beta, right? If you remember, this is the formula that we have used in this case to calculate this. Also, since we have borrowed 1 2 here, we have divided that 2 outside. Now if we rearrange, this 2 will become root 2. I have just rearranged it. Now this becomes VRMS, this becomes IRMS. Okay. And if you subtract alpha minus beta, you will get minus phi. Now cos of minus theta is cos theta, so that's why it is cos phi now, and it will become cos omega t plus phi, 2 omega t plus phi to be precise. Now we have to calculate the average power. Average power is most important in AC because here the current is going up and down, voltage is going up and down, they are varying. Sometimes it is positive, sometimes it is negative. So average power is the most important part in AC that we discussed in our yesterday's class. So here now you might think, sir, this is RMS, fine. Here is also cos, so average will be 0. No, this cos is a constant cos. This is a constant number. Constant number average is constant. I told you last class also, constant numbers average is constant. Okay, this term is varying with time. So there is a time dependency involved with this term only. This term has no time dependency. So if there is no time dependency, then when you are trying to find the average of this power, okay, so we can write VRMS IRMS times this cos phi. This term will become 0. So if you take average of this term, it will be 0. Average of only this term is 0. Average of cos phi is not 0. Cos phi is a constant. It will have a fixed value. So based on the given data, given values of omega naught, given values of L and C, phi will have a definite value, maybe 0 some cases. Okay, it may have 0 value, it may have pi by 2 value, but unless the value is not pi by 2, it will have a positive value. Okay, I am assuming it is 0 to less than obviously that angle. So in that case you can write that average power is VRMS IRMS cos phi, or P is equal to I square Z is also another formula, we know that. Okay, you can write in terms of that also, right? Now let us solve one numerical based on this. The average power dissipated in AC circuit is 2 watts. Okay, so average power dissipated in average power is given 2 watts. Okay, if a current flowing through a circuit is 2 ampere and impedance is 1 ohm, what is the power factor of the AC circuit? So power factor, we know that here this term cos phi is called power factor. This is called power factor. Okay, here also I square z cos phi should be there. I square is basically nothing but I RMS square. Okay, so I square is nothing but I RMS square, and Z is the impedance of the circuit. We know the formula because I RMS coming from the we know that I RMS is V RMS by Z. So you can use this and write this formula as I square Z cos phi. So that formula we are going to use here. Okay, so average power is equals to I RMS square. Let me write simpler words. Every time I RMS is boring. So I square Z cos phi. Okay, P is given 2 watts. I is given 2 ampere, and impedance is 1. So what is cos phi? Cos phi is called power factor because based on the value of cos phi, the power in the circuit changes, right? So that's why cos phi is called power factor. So it is basically 2 divided by 4, that is 1 by 2. So power factor is 1 by 2, that is 0.5. So don't confuse if you don't get the answer at the one glance. You have to check for the options. Okay, might be thinking, okay, I have solved 1 by 2, but 1 by 2 is not given, but 0.5 is given. So they are smart. They have given you an answer in a changed word. So you have to be careful. Don't mark 1 by root 2. Okay, 1 by root 2 may be closer to 1 by 2. So I will mark 1 by root 2. No. See the options once more. Read the questions carefully before answering. Now, resistive circuit, as I said, if the circuit contains only pure resistance, it is called resistive. Okay, in that case cos phi is 0. Okay, and cos phi is 1. Okay, there is a maximum power dissipation. So in this case phi is 0. So cos phi is plus 1. Cos phi plus 1 means what is the power dissipated? Power dissipated is I square Z or VI or VRMS, IRMS, whatever way you want to write. So maximum power dissipated. Why? Because the maximum possible value of cos theta is plus 1. So if the value of cos theta is 1, then the maximum power is dissipated. If the cos phi is any other value than 1, then obviously it is less than that. So we can assume that less power is dissipated. Let's check into the next observation. Purely inductive or capacitive circuit. If the circuit contains only inductor or capacitor, we have solved that in our yesterday's class. We know that the phase difference. So in case of purely inductive and purely capacitive, as we have seen yesterday's class, that the phase difference between voltage and current is 90 degrees. So 90 degrees means cos phi is 0. So if the phase difference is pi by 2, then cos pi by 2 is 0. So no power is dissipated. So purely inductive and purely capacitive circuits, no power dissipated. Okay, even though the current is flowing in the circuit, this current is sometimes referred as wattless current. So this is for basic information. Sometimes in your objective questions for PU especially, they ask you what is wattless current. So wattless current is when we are considering a purely inductive or purely capacitive circuit, the power dissipated in that circuit is 0. In an AC specifically in an AC circuit, when a purely inductive and purely capacitive circuits are considered, the power consumed is 0. So that's why it is called a wattless current. LCR series circuit. Now let us consider LCR series circuit. In LCR series circuit, power dissipated is given by P equals to Vrms Irms cos phi, or Vi, capital V capital I. Capital V capital I is nothing but RMS value. Okay, where phi is given by tan inverse XL minus XC by R. So phi may be non-zero in a RL or RC or RCL circuit. Even in such cases, power dissipated only in the resistor. So power resistor is the culprit. So resistor is only what he can consume. So basically you can consider resistor is someone who eats a lot. Okay, so he is eating only and he is absorbing the power. Okay, but capacitors and inductors, they do not consume any power. Okay, power dissipated at resonance in LCR circuit. Obviously in resonance it's simpler because XL minus XC becomes 0 and phi becomes 0. So cos phi is 1. So P is equal to I square Z or I square R. That is in resonance maximum power is dissipated. So as I said as before, that in resonance maximum power is dissipated, and that is expected because in resonance current is maximum. Right, so if you want to extract maximum current, obviously the power generated power absorbed will be maximum, right? Now let's solve one problem. A series LCR circuit contains inductance of 5 millihenry, capacitance of 2 microfarad and a resistance of 10 ohm. If a frequency AC source is varied, what is the frequency at which the maximum power dissipated? So this is basically a question based on resonance, but they have simply changed the language so that you might feel what is the value, how can we have to calculate the Z, etc. No, only thing that you have to calculate is first you have to calculate the value of omega naught. What is omega naught? Resonance frequency, right? So omega naught is nothing but 1 by square root of LC. Okay, now omega is 2 pi f, so 1 by root LC. Since they have asked you to find the frequency in terms of hertz, so if you see the options, they are all asked hertz, not in terms of angular frequency, that is radian per second. So you have to use this formula 2 pi root LC. Now let us put the values. So f is equals to 1 by 2 pi. What is L? L is 5 millihenry. 5 millihenry means 5 times 10 to the power of minus 3. Okay, and capacitance is 2 microfarad. 2 microfarad means 2 times 10 to the power of minus 6. Okay, now as you can see, it might appear that this square root will be difficult. Actually not. 2 pi, 5 to the 10, 10 to the power plus 1 minus 3 minus 6. Right, so what is this? 2 pi square root of 10 to the power of minus 8. So 1 minus 3 minus 6. So minus 3 minus 6 is minus 9, plus 1 is minus 8. Now square root of that, we can do square root of 10 to the powers or any number powers, but we cannot do if it is simply negative 8, right? Then it will become a complex number. So it will become 10 to the power of minus 4. So if you take this 10 to the power of minus 4 up, it will become 1 by 2 pi 10 to the power of 4 hertz. Now if you see the options, none of the options are given like that. They are all given only divided by pi. So how we can solve that? So what we have to do? We have to take 1 10 out and keep remaining 3 10s here. So 1 10 will cancel and it will become 5. So it will become 5 by pi times 10 to the power of 3 hertz. Now check the options. Which one is the correct answer? Correct answer is option C, 5 by pi into 10 to the power of 3 hertz. Okay, very interesting question, very important question. Okay, they have, instead of asking the question what is resonance frequency is, they have asked you at what frequency the maximum power will be dissipated. So that is basically the same question as if they have asked what is the resonant frequency. Okay, now in resonance previously there was a thing called Q factor. that Q factor is no longer part of the syllabus. Q factor is deleted. In fact, resonance, only the resonance frequency and the calculation is there, and that's graph is there. Calculations, any other derivations etc. related to resonance are not there, but resonance frequency is there and the graph is there. Okay, so resonance, even though the detailed explanation, application of resonance etc. are not there, but the resonance frequency calculations and the graph of resonance is still there. Q factor is not there. Now let's move into the last topic of today, that is transformers. So what is a transformer? Let us look into the definition of a transformer. For many purposes, it is necessary to change or transform an alternating voltage from one to another of greater or smaller value. So one voltage to another voltage of greater value or smaller value. Okay, this is done with a device called transformer using the principle of mutual induction. Now in the class, when I asked what is a transformer, one student rose up and say, sir, this is Optimus Prime. Okay, so Optimus Prime is a cartoon character, if you are not aware, but this is not the transformer that we are talking about. We are talking about electrical transformer, where we apply AC current. Specifically, it works for only AC current. It does not work for DC current, so you should be careful about that. And here one coil is called primary. In primary, we apply the external voltage. Okay, in primary we apply external voltage, and from there we collect. From here we collect the voltage. It is called secondary. So if you see there is a transformer situated outside your home or nearby your society, then basically what it is doing, the power supply that is in your city or in your locality, they are supplying a power supply of usually 440 volts. Okay, that 440 volt is reduced to 220 volt, and then it is being sent to your home, so that you can use that voltage, you can use that current and utilize all to work for your TVs, fans, lights, ACs, everything is working on that voltage. Okay, so the next time if you heard that thing that transformer is burned, that's why the power is not there, that means the transformer has malfunctioned and the coil inside the transformer has burned, so it needs to be replaced, and that's why it's taking some time. Now transformer, this is the simplest form of the transformer. Those who are going to study electrical engineering in future, or I think mechanical engineering as well, they will learn in detail about different forms of transformer, phase 2 transformer, 3-phase transformer. Okay, this is basically a one phase single phase transformer, very simple, but actual transformers are not single phase. There are minimum dual phase, in some cases 3 phases as well. Okay, so the transformer, what does it do? When you apply some voltage, say V in, okay, and the voltage is continuously changing. Okay, so continuously changing means the flux that is coming from this coil, okay, that it will generating a magnetic field, right? Even though I am showing the distance very large, actually their distance is not super large, and the frame is little bit bigger. Okay, they have only a small amount of gap, so that most field lines exiting the primary, they should interact with the secondary coil. Now when this input voltage is changing, okay, the flux linked with the secondary coil also changing, right? The magnetic field is changing. Magnetic field changing means flux linked with the secondary is changing. So flux linked with the secondary is changing means there is an induced current, right? So whenever you are changing the current associated with the primary, there is a change in the current coming out of the secondary. Okay, so this happens not in terms of current but in terms of voltage, but we will see what is the relationship between voltage, current, etc. So then this induces a voltage in the secondary, right? And that induced voltage we collect. right? So we know that if there is a coil placed in a magnetic field, there is a induction happens, okay, and then there is a induced voltage across that coil. So basically that same thing is utilized here. There are different types of transformer, different kinds of transformer. This is, as I said, this is the simplest form of the transformer, and where we apply the voltage is called primary, where we collect is called secondary. Similarly, if you see high tension wires, if you traveled across countryside of any places in India, you will see there are large columns, large poles. They are carrying very high tension wire, right? We call it high tension wire. Okay, they are actually carrying the current from the source. That is, if there is a power generation center, maybe hydro plant or any wind plant or any coal based plant, okay, there are many electric plants across India, okay, maybe a nuclear based plant. So from there the current is being transported to your cities, okay. So that poles, the high tension wires, actually transporting the current from the source to your home. Now this is not possible without having a transformer, right? So the voltage which is being generated in a hydroelectric power plant, they are very low. They are very low in the order of maybe say 5 volt or 10 volt or 20 volts, but they are in AC. So what you can do, you can step it up. This is called step up transformer. Okay, this is one example of step up transformer. I will tell you how you can identify that. So in a step up transformer, the voltage is increased from 5 volt to 1 kilovolt, very high value, okay. Then that high voltage is then transported, because if you transport high voltage, we know that power dissipated is basically V is equal to P is equal to VI, right? So if we keep the voltage high, the current will automatically remain less. In terms of voltage, we know that resistance is already there, right? So current will be less. If we increase the voltage, current, we can control the current. And in case of voltage only in terms of resistance, it is V square by R, whereas in terms of current, it is I square R. Okay, so even if you increase the voltage, resistance is also very high, so the power consumption will be less, right? Now if you increase the current somehow, okay, resistance is also high, then power consumption will be super high. So the wires that is carrying the current, they will heat up, they will burn out. Not only that, the power will exhaust even before it reaches your house. So to make sure that the power is actually received at the receiver's end, that is our homes, so they are being transported at a very high value. Okay, that is why it is called high tension wire. Not only because of the tension of the wire, because the voltage that they are carrying is very, very, very high. Okay, now once it is reaches to the local power stations, okay, local power stations, if you see outside every city there is a local power stations. In fact, you might have seen that if you travel by a train, okay, near every train stations there is a local power stations, okay, power stations, even they have marked it as a power stations. So what they do, they reduce the voltage from 1 kilovolt to 440 volts. Okay, then that 440 volt is being transported to different parts of the city. Now that 440 volt is being again reduced to 220 volt before it reaches to your house. So that final transformer outside your home is basically something which reduces the 440 volts to 220 volts. But the high tension wire, they are carrying much higher voltage than even 440 volts. So if you next time you see 440 volt danger, that means it is actually directly coming from the power station from your city. But if you move out of the city, you will see high tension wires, which is actually 1 kilovolt or above. Okay. So, and this fellow here sitting here quietly is doing the job of reducing that high voltage into low voltage. Again, at the power station, it is using the job of increasing the low voltage into high voltage so that it can be transported, right? So thank this little fellow if you are using electricity to watch this video. Okay. Now if the number of turns in primary is given by NP, okay, so let's look into what is the number of turns we are talking about. So this is the number of turns. So how many turns are there? 1, 2, 3. Okay, so 3 turns are here. So here NP, this is called number of turns in primary, NP. Okay, this is number of turns in primary, NP. How many rings are there? Okay, similarly the number of turns in secondary is called NS. Okay, number of turns in secondary is called NS. So this voltage applied in secondary Vs is actually calculated using this formula, Vs by Vp equals to Ns by Np. So Vs stands for V secondary, Vp stands for V primary. So V primary we are applying, Vs we are collecting, and they are based on this formula, Ns by Mp. Ns is the number of turns in secondary, and in terms of current, you can see that IPVP is equal to ISVS. So what is the meaning of that? What is IPVP? IPVP is the power applied in primary, and this is the power received in the secondary. So I have written it in a reverse order so that you can understand that power is Vodafone Idea. So Vodafone Idea Vodafone in this case, right? So Idea Vodafone, right? So thus the power input is equals to power output in an ideal transformer. Now the transformers that we use in our real life are not ideal. There are some flux leakages, there are some different incidents happening inside the transformer. So you can not get 100% power conversion. Some power is lost from primary to secondary conversion, but mostly it is like suppose even if we consider 70-80% conversion, that is a good conversion, right? Now let us solve one more numerical. An ideal transformer has a turns ratio of 10. What is the turn ratio? Turn ratio is number of turns in secondary divided by number of turns in primary. So you need to remember that turn ratio means secondary by primary. Okay, turn ratio is 10. Okay, when the primary is connected to 220 volt 50 Hz AC source, the power output is. So they have asked you to find the power output when this is connected to a source. Okay, now you should remember that power, you cannot increase or decrease the power. Power is like the main thing. Okay, even if you increase the voltage, even if you decrease the current, power will remain the same. Okay, so power is equal to the power input. Output power will always be equal to the power input. Only thing you can change is the voltage, only thing you can change is the power loss, but the power that you are inserting into the primary of the coil, the same power you can extract from the secondary. Power you can consider as energy. You can consider power is the because we know that power is basically a form of energy, like how much work you can do in a 1 second. So if you multiply power with time, basically that converts into an energy. So that is why power cannot be created or destroyed, right? So power has to remain constant, right? So power equals to power input. Okay, some power is lost in the form of heat, that is separate thing, but ideal transformer no loss is happening. In that case you have to write it, power input is equals to power output. Now this is the homework questions, and if you have any other questions related to the topics that we are discussed today in our class, you can mention that in the comment below. And this is the homework question. You can pause the video, you can answer the question and mention the answer in the comment below. So this question let me explain it to you. A step up transformer. Step up transformer means when we get the output more than that of the input voltage. Okay, so for example, I told you the example where we are increasing the voltage in the power source, power station. So the step up transformer is used in power stations where 5 volt is converted into 1 kilovolt. Okay, so that is a step up transformer. Okay, a step up transformer operates on 230 volt line and load current of 2 ampere. The ratio of the primary and secondary windings is 1:25. Then the current in the primary is. So they have asked you that step up transformer operates on a 230 volt line and the load current, this is the input voltage. This is input voltage. Load means output. Load always means output. Okay, so input voltage is given and output current is given. Okay, the ratio is given. So then the current in the primary is. So they have asked you to find the current in the primary. Now you can solve this even without using the voltage, simply using current you can solve it. So if you I have given you enough hints, I have given you enough formulas, try to solve it, let me know the answer, and I will be back with the answers in day after tomorrow's class, because tomorrow we are going to do PYQs. Maybe in PYQs this problem will be there, we will solve it, maybe not, let's see. Now this is also very important question. An inductor of inductance L and resistor R are joined together in series and connected by a source of frequency omega. The power dissipated in the circuit is. So here inductor and resistor are connected. So it's a LR circuit or RL circuit. Okay. What is the power dissipated in the RL circuit? That was the question. Simple question. I hope you can answer that and mention the answer in the comment below. Okay, if you simply follow the steps, you will be able to answer that. Now if you are wondering from where you can get all the videos, all the lectures, it is available in our channel as a playlist form. You can go to the playlist, bookmark that playlist and see all the videos. Whenever we are uploading a video, it will be given you as a notification that a new video is added. Okay, every day 9 PM we are doing one physics video, and every day it is coming, and except Sunday, because Sunday, as you know, is the time for KPL. So if you still have not bookmarked this page, please bookmark, and that will help you to study and score good marks for your upcoming KCET exam. And also join our WhatsApp family. Here we have a very active people. We are posting all the videos. Whenever we are dropping a video, it is being posted in our WhatsApp group, so you can get the notification. Now if you think that this video is helping you, share it with your friends, and don't forget to subscribe to our channel. Thank you for watching.